We are finishing with Chapter 8 on elimination reactions today. And I want to just do one more example before we move on. And this is an SN1 and E1 example. So here's a starting material that I think you've done a problem before on. Here is a nucleophile, MEOH, methanol. Hopefully you're okay with abbreviating CH3 as ME. We tend to do that in OChem, and it's fine. You can write out CH3 if you want to. You can use ME as an abbreviation. It's fine. If you were to look at this, you would say methanol is a weak nucleophile and a weak base. And then if you looked at the alkyl halide, you'd notice that it's secondary. And so you'd notice that SN1 and E1 are possible. And you'd also notice that the nucleophile methanol is the kind of nucleophile that has to wait for the leaving group to leave. So leaving group leavingness is possible here for two reasons. First, because it's a secondary alkyl halide. But then the other structural clue is that the leaving group is at what we are going to call an allylic position. That is a word we use in OChem to mean adjacent to a pi bond. The allylic carbon is adjacent to a pi bond. By the way, another word we use for a carbon involved in a pi bond is our carbon-carbon pi bond is a vinyl carbon. Not that important, but if you hear me say vinyl carbon or allylic carbon, it would be useful for you to know what we're talking about. Vinyl, allyl, vinylic, allylic, both words that we will use. So when the leaving group is at an allylic position, that's the structural clue that you could have a resonance stabilized carbocation. So if we draw the leaving group leaving as I've done here, and then draw the two carbocations that could form, one of them is this, and then the other is the other resonance structure, where the pi bond moves over here, and then the positive charge is here. Now, you could have some argument about whether the positive charge is more on the secondary carbon versus the tertiary carbon. We're not going to have that argument. We'll simply expect it to be in both places because it is, because of resonance. And we will consider SN1 and E1 products from both resonance structures. And the SN1 product should be pretty easy. I will show you them real fast. Methanol would attack the empty p orbital on the positively charged carbon from above or below. And if we attack the resonance structure on the top, we're going to get this product. Now, I'm choosing deliberately to not use dashes or wedges there. When I do that, that should communicate to you that both stereochemical configurations are present. In other words, when you don't use dashes or wedges on a carbon, that doesn't mean that you communicate all the bonds are in the plane of the page. We're assuming that you know what an sp3 hybridized carbon is and that you know what tetrahedral geometry is. The lack of the dashes and wedges communicates that either it's not a stereocenter, so it doesn't matter, or if it is a stereocenter, you have both configurations present. So to draw this product this way is exactly the same and equivalent to drawing both of the possible stereoisomers. And that's something that you are free to do. You are free to represent both configurations of a single stereocenter by just not using dashes or wedges. Okay? Of course, the SN1 product for the resonance structure below would simply be this one, though it represents two products, right? Two stereoisomers. All right. Now, the other thing we need to consider is the possibility of an E1 reaction, because as I've said, SN1 and E1 compete with each other. So we need to look for protons that are beta to the positive charge. So in an E1 reaction, you are looking for protons that are beta to the positive charge. But not only that, they have to be able to line up with the empty p orbital that is the LUMO of the carbocation. That's a requirement so that sigma to p hyperconjugation can occur. Remember, that's what allows the LUMO to spread out onto the beta proton in the first place. So if the beta proton can't line up with the empty p orbital, it can't have any LUMO on it, and it is therefore not reactive. So let's illustrate this with the resonance structure on the top. We have two different beta carbons, two different carbons that are beta to the positive charge. One of them is just a normal secondary carbon, and the other, the orange one, is a vinyl carbon. So on the regular blue beta carbon, you have two protons, HA and HB. And then on the orange vinyl carbon, you have this vinyl proton, orange proton. We'll call it HC. Now, I'm just going to draw the empty p orbital that is implied, that is on this positively charged carbon. One lobe will be up, above the plane of the page, and one lobe will be below the plane of the page. Now, HA, which is a wedge, can line up with the pink lobe of the p orbital, so it can participate in hyperconjugation. And HB, below the plane of the page, can line up with the orange lobe of the empty p orbital, so it can participate in hyperconjugation. In other words, we expect both HA and HB to be reactive in an E1 reaction. Now, because this is in a ring, you get exactly the same product whether you remove HA or HB. So there's nothing to worry about there in terms of if I remove one versus the other. Let me show you what the mechanism would look like. Our weak base is strong enough to remove a proton that is beta to a positively charged carbon. So if we remove HA, we're going to get the blue elimination product, which would look like this. Okay, now what about HC, the vinyl proton? It turns out that HC, if you look at the way we've drawn it, HC is on an sp2 hybridized carbon in the plane of the page. And you might say, okay, fine, let's just rotate it outside the plane of the page to line it up with the empty p orbital. Not so fast. Remember that this is a resonance stabilized carbocation. It's not drawn here, but on each of these carbons, the two vinyl carbons, there are p orbitals that are participating in this pi bond. And resonance implies that those p orbitals here are lined up with this empty p orbital there. I could draw that briefly. It would be something like this. If those p orbitals on the vinyl carbons were to twist out away from being lined up with the empty p orbital on the positively charged carbon, you would lose the opportunity for resonance. It turns out resonance always involves lining up of p orbitals on adjacent atoms. And if you twist or break that alignment out of parallel, you break resonance, and that's destabilizing. So it turns out that the HC, the vinyl proton, is permanently perpendicular or orthogonal to the empty p orbital, and therefore it is not reactive in an E1 reaction because it can't do sigma to p hyperconjugation. All right? Yes?
If there wasn't any resonance stabilization here, how would you be able to rotate it to make it long?
So your question, what if there wasn't any resonance stabilization? The only way to get rid of resonance stabilization would be to get rid of that double bond And then there would be 2 protons on this carbon just like they are on that one, and then you just proceed as normal. Yep. Okay. Yes?
But even if there was 2 hydrogen on that side, then couldn't you, like, would you still have to draw that there's an option for double bonding? Like, it would be on the left side or the right side of the ring?
Are you asking a question about the hypothetical molecule I was drawing? Okay. So, stepping aside from that hypothetical molecule, if the molecule were like this, then yes, you would expect to get a blue elimination product and an orange elimination product like that. Okay. And also, sorry, I think that was a hydrogen. I don't know. Whatever. Okay, so there's only H blue A and H blue HB that can participate in the E1 reaction. So this is the only elimination product we expect from this carbocation. If we look at this one, we've got a similar situation. Here's a vinyl proton. And then on this carbon, we have 2 protons in green that can line up with the empty p orbital. And then on this carbon, we have 3 protons on the methyl group that can line up with the empty p orbital. I'm not going to draw that empty p orbital on this intermediate. I'm assuming that you can visualize in your head that it's above the plane of the page and below the plane of the page. I'm assuming that you can see how either of the green protons could line up with that empty p orbital, not the vinyl proton, and then by rotation around the carbon-carbon bond here, any of these methyl protons in purple could line up with the empty p orbital. Of course, as long as one of them can, then you get the product, and there's only one product, elimination product possible there. So I'll draw the 2 elimination products you would expect from this intermediate. Here's the green one, and then here's the purple one. And I'll just draw in the 2 other hydrogens there to make it absolutely clear what we're talking about. Okay, so on an exam, you would need to select as products of this reaction 1, 2, 3, 4, 5, because remember that's 2 stereoisomers, 6, 7. 7 possible products. I would likely have shown, instead of just using no dashes or wedges, I would likely have shown both stereoisomers like this, because I would want to give you the chance to show that you understood that this mechanism was SN1 and E1 rather than just SN2 or just E2. For example, if these were options A through H or whatever, 7, A through G, maybe? Anyway, if you picked this one, which we'll call option B, if you picked that one and only that one, that would indicate that you thought the mechanism was SN2, right? And if you picked the blue one and only the blue one, that would indicate that you thought the mechanism was just E2. And if you picked B and C here, or just this stereoisomer and then the blue elimination product, that would indicate that you thought it was a mixture of the SN2 and E2 mechanisms. Or if you just picked the SN1 products, that would indicate that you forgot that SN1 and E1 compete. So anyway, even with all of these answers, which are right, when the question is select all that apply, there's a lot of ways to get some of the right answers, but not all of them. Yeah?
When talking about all the E1 products, in the textbook we talk a lot about like minor and major products.
Sure.
Which one of these, because 2 of them look pretty similar, which
Right.
one would be the major
as I look at blue, green, and purple elimination products, the way we're trying to determine which one's major versus minor is stability of the alkene, which is how substituted it is. Both blue and green have a disubstituted alkene and a trisubstituted alkene, so I have no way of saying which one's more stable there. The purple one has 2 disubstituted alkenes, so I can at least say that the blue ones are probably more stable and maybe form in a larger amount than the purple one. I'm not going to try to figure out any more selectivity beyond that. And for this question, I wouldn't have even bothered. I'd just have you select all the products. Yep. Okay. Yeah, and probably I would have also thrown in some bogus products that aren't even like, couldn't even be right ones. In the 8 a.m. class, they asked me to draw some bogus products. I was like, okay, I don't know. So then I started doing weird stuff like this and like it was unclear how that, you likely would not have been deceived by those, but yeah, so. But I tried to illustrate how even seeing correct products is a problem, because if you don't know that the mechanism is SN1 and E1, you might select some of the right answers, but not all of them. Okay. More questions on that? Okay. So we now move on to chapter 9. Now, I scared somewhat at 8 a.m. because they were like, hold on, we just barely did problem set 7. How are we already moving on to chapter 9? And I tried to reassure the student by saying that the problem sets are named according to the week, not the chapter. So you just did problem set 7 that covered chapters 7 and 8. Probably in your recitation section this week, you were mostly worried about the exam, so probably you focused on the chapter 7 portions of that problem set and not the chapter 8 portions. I'm going to make a problem set 8, which will include some stuff from chapter 8 and some stuff from chapter 9. So it's awkward to have a problem set that's due at a specific time that doesn't neatly coincide with when we finish chapters, so we're just doing our best. But don't freak out. The number of the problem set has nothing to do with what chapter we're on. Okay. So chapter 9, there are 2 main themes in chapter 9. Chapter 9 is about substitution and elimination reactions with alcohols. But one major theme of chapter 9 is the travails of SN1 and E1 reactions. Basically anything that involves carbocation intermediates. There are problems associated with carbocation intermediates. The first one is obvious, and that is just to look at that example we just did. 1 starting material, 7 products. Now, when you take the organic chemistry lab 353, you're going to be doing reactions which lead to hopefully just 1 product, or maybe 1 or 2, and you have to separate them from each other. It will be hard to separate 2 things from each other. You will be frustrated by that process. Imagine trying to separate 7 things from each other, and things that are pretty similar. Imagine trying to find a way to get just the blue alkene and not the green alkene. Basically, from a synthetic point of view, the SN1 and the E1 reaction are a big problem and a waste of time. And notice that the mixture of products you get is a direct consequence of the fact that your intermediate is a carbocation. The first part of this you've thought about for several days now, and that is stereochemistry. You're going to get both stereoisomers if you go through a carbocationic intermediate, if you make a stereocenter in your product, because the empty p orbital can be attacked from above or below. The second problem is, of course, multiple beta protons and getting multiple elimination products. So we're going to be thinking about in chapter 9 how to avoid a carbocationic intermediate so that we can avoid this multiple product situation. And another way of saying this is chiral starting materials are really expensive. And so it would be the most boneheaded thing you could do to buy this chiral starting material and then say, I want to do an SN1 and E1 reaction on this. That is a waste of hundreds of dollars because you go through an intermediate that's not chiral. Like if you want to do it, fine, but save yourself some money and buy the racemate. The stereochemistry doesn't matter and goes away once you get here. Or that being said, alternatively, if you absolutely want this product where you have just one stereoisomer, you need to do an SN2 reaction, not an SN1 reaction. So avoiding a carbocationic intermediate, if we can, is going to be an important theme. So what are the travails of the carbocationic intermediate of the SN1 and the E1 reaction? First is loss of stereochemistry. Related to that, and sometimes because of that, multiple products, especially a mix of SN1 and E1 products. And then there's another issue which is worse than these first two issues. This is one that is new that you haven't encountered yet. It should have been happening during chapters 7 and 8, but we deliberately avoided talking about it. We chose examples where it wasn't going to happen to make things simpler. Now we're going to pull back the curtain and show you the problem in all of its gory detail, and that is the evil specter of carbocation rearrangement, which I'm going to illustrate for you at the end of class today. But we need a house band to do the dun dun dun, and we need some thunder when I say carbocation rearrangement, right? So that's a challenging one, and I'll show you why it happens and when it happens and give you tools to deal with it. Then the second, so theme 1 of chapter 9 is avoiding the carbocation. Theme 2 is related to theme 1, and that is in chapter 9, our starting material is going to be an alcohol or an ether. And if you look at the alcohol, if I made an alcohol like this, if I wanted to do substitution and elimination chemistry with alcohols, I've got a problem. And the problem is that OH is a bad leaving group. So good leaving groups, as you know, are conjugate bases of strong acids. Another way of saying that is good leaving groups have conjugate acids with pKa's that are less than 0. So to evaluate whether OH minus is a good leaving group, simply draw it as it would appear if it left with its electrons. So that's OH minus. Then you draw its conjugate acid, H2O, and the pKa of that is 16. So that is a terrible, horrible, no good, none of you read that book, did you? No good, yeah, very bad leaving group. And that is something that's actually useful to remember. That concept that OH minus or OR minus are terrible, horrible, very bad, no good, very bad leaving groups is something that we'll come back to again and again in 351 and 352. Both OH minus and OR minus are really bad leaving groups. So, one theme of chapter 9 is how to deal with a cruddy leaving group. And one strategy is to turn that frown upside down by converting the good, poor leaving group into something that's a better leaving group. All right? So that will be a major part of chapter 9. Our first strategy for turning the OH into a better leaving group is the simplest one, and that is protonation. So imagine you take your alcohol and you add some kind of acid that has a pKa that's low enough that you could reasonably expect the alcohol to deprotonate the acid. That would form the conjugate base of the alcohol, which is this oxonium ion. And then you'll have the conjugate base of your acid, which we're just being generic about. Now, suddenly, protonation has turned that leaving group into a much better leaving group. Let's illustrate that by just drawing what it would look like when it left. That's H2O. Its conjugate acid is hydronium, whose pKa is -2. Now that is a fire leaving group. Did I use that? Yeah. You're surprised that I know that one, right? That is a fire leaving group, so we will add the flames. Yep. And now it's possible to do substitution and elimination chemistry there. So protonation you can use to turn OH into a better leaving group. So let's try to play this out, this strategy out, and see how well it works. We'll start with this alcohol, and suppose that my desired product, my goal, what I want to make, is I want to replace the OH with Cl. And I want Cl to be a dash instead of a wedge. Based on that, what kind of reaction do you think I want to do? Right, if I want inversion of configuration and I want to just get one stereoisomer, my preferred strategy would be SN2. All right, well, let's try this approach and see whether it works. We would use HCl, and the idea is that HCl would first protonate the alcohol to convert it into the fire leaving group, and then the conjugate base Cl minus could attack the carbon and displace the good leaving group and get the product. Decent idea, but it turns out that what we actually observe, instead of the preferred SN2 product, what we actually observe in this reaction as products are both the desired stereoisomer and the undesired stereoisomer, which tells you that the mechanism had to be what? Yeah, it tells you had to have gone through an SN1 mechanism, had to have been SN1 with a carbocationic intermediate. Now, if the mechanism was SN1, I just got done telling you that SN1 and E1 always compete. Nevertheless, for this reaction in your text says we don't observe elimination products. And that makes me uncomfortable, but it's also the truth. you would have expected if you had to go through an SN1 mechanism, you would have expected to go through this planar carbocationic intermediate, and then you would have expected the nucleophile / base to attack from above or below at the positively charged carbon to give you both of these products. I get that, but the question is, why doesn't Cl- attack any of the beta protons? Because we've been trained to expect that. And we don't have a good answer for that here. You're gonna find, especially in chapter 9, that things that you expect to happen based on the chart that I gave you for chapters 7 and 8 sometimes don't always turn out the expected way. There will be, and that's just reality. Sometimes reality is more complicated than we expect. Usually when that happens, there's a deeper underlying principle that we don't totally understand or haven't learned yet. Sometimes we'll go on and learn that principle. Other times it won't be worth our time, so we'll just deal with the complexity as it is. And this is kind of one of those times. Why don't we observe E1 products? Well, I suppose if you want a hand-wavy explanation, it is that Cl- is a complicated story as a nucleophile. If you looked at what we said before about what a good nucleophile was and what a good base was, we said that good nucleophiles have conjugate acids with pKa's greater than 0, and that good bases have conjugate acids with pKa's greater than equal to 16. So we would have said, based on what we did in chapters 7 and 8, that Cl- was a weak nucleophile and a weak base. So we would have predicted SN1 and E1. The story gets a little bit more complicated though. And this has to do with something in chapter 7 that we didn't talk about. And that is that Cl- and Br- and I-, despite the fact that their conjugate acid pKs are so low, they can be decent nucleophiles. And part of this has to do with their size and how easily they escape the cage of surrounding solvent molecules. This is more of an issue in protic solvent that can hydrogen bond with the anion. We didn't talk in a lot of detail about protic versus aprotic solvents in chapter 7, mostly because it didn't really move the needle from whether the reaction was going to be SN1 or SN2. But solvent does play a role in how nucleophilic things are. And you can run reactions under conditions where chloride, iodide, and bromide are actually decent nucleophiles. So from now on our list, we can include chloride and iodide and bromide as things that are never good bases, but they can be good nucleophiles. But even then, again, if it's a good nucleophile, why does it wait for the leaving group to leave? Why is the reaction SN1 and I got nothing? The evidence says that it is. And so it must be that they're okay as nucleophiles, but you have to coax them into reacting. Yeah?
When you say coax them into reacting, what determines that? Is it
Well, I'm just saying that if you were to say that they are a good nucleophile, then there's no way you would expect to see the SN2 products, because you would be, why doesn't it just attack first?
Right.
And the answer must be that they wait for the leaving group to leave. Yeah. Yes?
How come fluorine minus isn't on that list?
How come F- isn't on the list? In part, we won't use HF as an acid to protonate an alcohol because its pKa is too high. HF is actually not a strong acid. Yeah. Okay. So, what you learn from this first strategy is, yes, we turned the good leaving group, we turned the cruddy leaving group into a good leaving group, but apparently either the leaving group was too fire and it left too fast, or the nucleophile was not strong enough And so we got a mixture of SN1 products anyway. As to why we didn't see any E1 products, that we're just going to have to memorize. But it turns out that if you do these similar experiments with other alcohols, the general trend is that secondary and tertiary alcohols proceed via SN1 with HBr, HI, and HCl. And you don't see elimination products. It turns out that for a primary alcohol, SN1 is not an option because a primary carbocation is too unstable. So the only possible mechanism is SN2, but it is slow. And again, this must reflect the fact that, say, Cl- is not a stellar nucleophile, so that once you protonate the OH group, it takes Cl- a while to attack the sigma star and get rid of the leaving group. Okay. And I'm sorry that chemistry is as complicated as it is, but welcome to adulthood. Your whole life is going to be complicated with things that didn't go as expected and things that are not as cut and dried simple as you thought they were going to be. And just welcome to the club. It's good to have friends in this club on the boat of complicated lives. I've been here for a long time, and now you're here with me, and it feels good to have company. Okay, so speaking of things that are more complicated than you wanted them to be, let's deal with carbocation rearrangement. Dun, dun, dun. All right, so here is a secondary alkyl halide. I will teach you in a little bit how to recognize this molecule as a situation where carbocation rearrangement could occur. Let's use HI to protonate the OH, turn it into a good leaving group, and then you would expect the leaving group to leave to give you a carbocation. So we're skipping a couple of steps. That carbocation would look like this. And then you would expect I- to attack the carbocation from either above or below, and you would expect to get these two products, these two enantiomers. And in fact, you observe both of them, so yay. But along the way, you also observe this. Yeah. What witchcraft is this? Yeah? If you look at what's happened, in our starting material, we had a quaternary carbon, that is a carbon bonded to four things, 3 methyl groups, and then a CH2, or another carbon. And then we had a secondary carbon bonded to only 2 other carbons with the methyl group over here. And all of those methyl groups are in the right place in what we are going to call our non-rearranged products. We'll highlight these methyl groups in pink and this one in blue. And the pink methyl groups are still in the right place here, but it turns out one of them has moved over in what I will call the rearranged product. And right now, that should just sort of be shocking, and you should be like, I thought we couldn't just pop carbons off and stick them back on in new places. And the answer is you can't, but something is going on here with the carbocation that you need to be aware of. So what we're going to do is draw this carbocation from the side. We're going to draw the bond between the carbon and the positively charged carbon. Here's the methyl group. Here is the hydrogen. the positive formal charges on that carbon, and I'm going to draw the empty p orbital that's on that carbon. All right. And then we're going to draw the adjacent carbon where the methyl groups are. We'll draw one of them lined up with the empty p orbital, and we'll draw the other two pointed down towards the bottom of the page, but coming out at you and then back away from you, respectively. Okay? So this is what that carbocation looks like. Now, it turns out you've seen hyperconjugation before when this group was a hydrogen, but hyperconjugation can also occur for things that are not hydrogens, say methyl groups. So I'm going to draw just a portion of the carbon-carbon sigma bonding orbital. And you can see that this filled carbon-carbon sigma bonding orbital is lined up with the empty p orbital and participating in sigma to p hyperconjugation. Now remember, one of the consequences of hyperconjugation is that the electrons in this bond spread out a little bit towards the empty p orbital. And they smear out a little bit in space. And if the electrons in that bond are smearing around in space, it's not such a stretch to think that the methyl group might start to lean over with the electrons. So let's just imagine that the methyl group starts to move a little bit towards our right in the direction of where the electrons are going because of hyperconjugation. Perhaps at some stage, as the methyl group moved, we might go through what I will call a transition state that looks like this. Where the methyl group is actually sort of evenly shared between the two carbons. You could call this a transition state. There's actually some evidence that in some cases this is actually an energy minimum, where you have three atoms, the two atoms that are here and then the methyl group, that are each sharing 3 electrons, almost as though, if you were to sort of draw what the orbital looked like, almost as though the 2 electrons are kind of like a pi bond, and the methyl group is sort of sitting down on the pi bond. Okay, and then imagine that the methyl group continues to move over to the right, and eventually forms this structure where now the electrons are completely here. And now the positive charge is completely over here. Oops. Yikes. That's called carbocation rearrangement. And this process overall is called going through a 1,2 methyl shift, because the methyl group, we're going to say, was on carbon 1, and afterwards the methyl group is now on carbon 2. So this is something that can happen with carbocations. It happens here because if you look at the carbocation before the rearrangement, it is a secondary carbocation. After the rearrangement, look where the positive charge is. It is on a tertiary carbon. So after rearrangement, we can form a more stable tertiary carbocation, meaning this rearrangement is actually downhill in energy. Okay. Yes?
Because it's downhill, it's not interchanging, going back and forth.
So how downhill is the question. We're going to view it as though it's an equilibrium, and I will want you to draw both rearranged and non-rearranged products. Your text may have you just draw rearranged products, and they're doing that just to have you go through the process of rearrangement. So we're out of time for questions. You can come down and we'll talk. I will see you Monday. We'll pick up with carbocation rearrangement then.